So today I want to start going over gas laws. So the laws that we'll be going over will describe how gases behave. And if we look at the kinetic molecular theory, we can predict the relationships that they will show. What we will see is the amount of change that will happen to a gas can be calculated with mathematical equations. Okay, so the first law we're going to be going over is Boyle's Law. And this is only true at constant temperature and the constant number of moles. So that means the amount of gas cannot change for this law to be true. What we see with Boyle's law is that the gas pressure and volume are inversely related, which simply means as one goes up, the other one goes down. So the formula that we're going to be using for this law is P1 times V1 is equal to P2 times V2. Okay, so what I have on this graph here is a relationship described by Boyle's law. What we see on the y-axis is we have pressure. On the x-axis, we have volume. As the pressure increases on the y-axis, we see that the amount of volume decreases and vice versa. Now I'm going to show you a video with a bell jar, and a bell jar is going to reduce the pressure in the container by using a vacuum pump. All the while, the amount of air in the balloon is staying constant. However, the pressure surrounding the balloon is decreasing. So I want you to see what happens to the volume of the balloon as this occurs.
In a demonstration of Boyle's law, we will place the balloon in a vacuum bell jar. We will apply a vacuum which basically pumps out the air in the bell jar. The pressure outside the balloon will be greater than the pressure inside. The balloon expands to try and equalize the pressure. Volume and pressure are inversely related to each other. When we release the vacuum, the pressure increases and the volume decreases. As another demonstration of Boyle's law, we will put a marshmallow peep into our vacuum jar. The marshmallow contains air trapped in a mixture of gelatin and sugar. As we apply the vacuum, the pressure outside is lower than the pressure inside. The air in the peep will expand to try and equalize the pressure. When we release the vacuum, the pressure increases and the volume decreases. As another illustration of Boyle's law, we will put some shaving cream into our vacuum jar. The shaving cream contains air trapped in a soap mixture. As we apply a vacuum, the pressure outside is lower than the pressure inside. The shaving cream will expand to try and equalize the pressure. As you decrease the pressure, the volume increases.
Okay, so now we're going to do a problem with Boyle's law, and this is the worksheet that you guys have for homework. This is a mixed gas laws worksheet, and I will go over which problems you have to do. But I want to show you one of these problems. I'm just showing you the technique I want you to do as you're solving it. So let's go down to number 3. And when you're doing these problems, because they are all mixed up, it's very important that you first analyze the problem so you can correctly determine exactly which law you'll be using, and also so you can make sure that your units from one condition to the other are constant, that you're not dealing with different units. So in this problem, we have a volume, so that's going to be our V1 is equal to 150 milliliters. And then it says when its pressure, so this goes with this volume, so these two go together, P1 is equal to 440 millimeters of mercury. I also want in your table to put down T, and then you have V2, P2, and T2. So let's look at the next conditions. If the pressure is increased to standard pressure, remember standard pressure is 1 atmosphere. And if you remember, 1 atmosphere is 760 millimeters of mercury. It's telling you the temperature remains constant, so we can get rid of the temperature in this table because it's not changing. And then it's asking, what will the new gas volume be? So it's saying, what is this? Okay, so we're going to solve. So we see we only have V1, P1 is equal to V2, P2. This is Boyle's Law, so we know we're using Boyle's Law. So by looking at what information they're giving you, you can also determine which law you're supposed to be using. So with Boyle's Law, we do not have to have the pressure and volume in any particular units, but we do need to make sure that we have the same unit throughout the problem. So we have millimeters of mercury for both our initial and final pressure. We're not asked to find the volume in each particular unit, so we don't need to worry about getting the 150 milliliters into a particular unit, so we could start plugging this information in. So we have 150 milliliters times, and then 440 millimeters of mercury. We have our V2, which is our X, times 760 millimeters of mercury. Now remember, to get V2 by itself, we have to undo the operation, which is multiplication on each side. We're going to divide by 760 millimeters of mercury on each side of our equation. Okay, so this will get rid of 760 millimeters of mercury. So now we're going to take 150. You notice that millimeters of mercury cancel out, so we're going to do 150 times 440 divided by 760. And this gives us 86 point, and this is actually two significant figures, so I'm actually going to round this to 87 milliliters. So you notice here the pressure is increasing. So remember, the relationship between pressure and volume is that as pressure is increasing, the volume should decrease. And that's exactly what we're seeing. So this answer makes sense. And if you look at this worksheet actually does give you the answer, so you could check your work by checking your answer there. Okay, so that's a Boyle's Law problem. So now we're going to do Charles' Law. Okay, so the next law that we're going to be going over is Charles' Law. So this law says that the volume of a gas is directly proportional to the Kelvin temperature. This is underlined because your temperature has to be in Kelvin for this law to work. And for this law, we're holding the pressure and the number of moles constant. So if you see here, we have V1 over T1 is equal to V2 over T2. Now remember, temperature can be 0, so in the Celsius scale, and if that were the case, you would get an invalid answer if you tried to put that into your calculator. Also, temperature can be negative in the Celsius scale, and there's no such thing as negative volume. These are some of the reasons why temperature has to be in Kelvin instead of Celsius. So I want to show you the relationship for this law. And what this law is, this is a direct relationship. That means as one goes up, the other one also goes up. And we see here that as volume increases, so does temperature. So before we do a problem, I first want to show you a video that I made last spring during our lockdown that illustrates Charles' Law. And then we're going to do a problem with Charles' Law. Well, today what I'm going to do is do a demonstration of Charles' Law. And I have some ivory soap here. And the ivory soap, if you guys don't know it, does float in water. And the reason why it floats in water is because it has little pockets of air inside the ivory soap. And we're going to be putting a small piece of this ivory soap into the microwave, and you guys can see what happens to those little pockets of air that are inside the ivory soap. So as you see, I just cut off a small amount of this. So if you want to try this at home so your parents don't kill you, make sure you're using a small amount. So now we're going to put this into the microwave. And We're going to cook it for about 30 seconds on high. And maybe you could bring that over closer to the microwave so maybe they could see what's happening inside the microwave.
Ooh. Wow.
So I think that's it. I don't see it expanding more, so let's take it out and look at it. Oh my gosh, look at that. Does everybody see this? This is ivory soap. So what happened is that as we increase the temperature inside the microwave, the little pockets of gas in the ivory soap expanded. And now we have nice fluffy ivory soap, and it will stay like this. Really cool. So thank you so much for watching.
Does it still work like soap?
Yes, it does. You can use this, Alyssa. So thank you. That's it. Okay, so let's do a Charles Law problem. So whenever you're doing these problems, I want you to make sure that you first set up a table. So we have P1, V1, T1, and then P2, V2, T2. The reason why I want you to make sure you're setting up a table is these problems are all mixed up. This is going to help you to kind of sort through which kind of problem you have, and also to make sure that your units are matching from one set of conditions to the other. So we see that we have a volume of 752 milliliters, and this is at 25 degrees Celsius. This tells you that these two, the way it's worded, these two go together. It says what temperature, so we don't know this second temperature, and then it's placed in a 689 milliliter container, and then the pressure is remaining constant. So we can get rid of our pressure since that's not changing. Also, if the problem did not mention pressure, we can assume it was staying constant. So we see that we're just left with volume and temperature, so that tells us we're using Charles' Law. So V1 over T1 is equal to V2 over T2. Now, Charles' Law, and really any gas law, says that temperature has to be in Kelvin. So we're going to have to get this temperature into Kelvin by adding 273. So this gives us 298 Kelvin. So we have our initial volume over our initial temperature is equal to our final volume over our final temperature, which we're trying to find. Now, when T2 is being solved for, it's in the denominator, so we're going to have to cross multiply to get T2 by itself. This is going to give us 752, and we can also get rid of those milliliters since they're on both sides, times T2 is equal to 689 times 298 Kelvin. So now to get T2 by itself, we're going to divide each side by 752. Now, when we solve for T2, we're going to get 689 times 298, divide that by 752, and that gives us T2 is equal to 273 Kelvin. And if we look at it, we can check our answer. This is the same as what we were given. And we can also think about it. Here, the volume is going down. Since these are directly proportional, if the volume is decreasing, the temperature should also be decreasing, and that's what we see. So now we're going to go over Gay-Lussac's law. So Gay-Lussac's simply has the temperature and the pressure are directly related. And for this law, the number of moles in the volume are being held constant. So the formula that we have is P1 over T1 is equal to P2 over T2. So again, temperature has to be in Kelvin, just like any other gas law, has to be in Kelvin. And the relationship here is also a direct relationship. So we see here as pressure goes up, temperature also goes up. Because the problems for Gay-Lussac's are very similar to Charles' law, I'm not going to work through a problem. You're just going to notice that you're going to have pressure and temperature instead of volume and temperature. And again, temperature has to be in Kelvin, and you just have to isolate the variable you're looking for. Okay, so now I just want to show you something to help you to kind of think about your gas laws. So in class, I had the students make these. For those of you that are at home, you should try making this. It's a card, and you should put 3 holes on the bottom. Put it in this order P, T, V. And the way this works is if you have, for example, Boyle's Law, where temperature is being held constant, you could put a pencil through the T. And if you notice, as pressure increases, that side of the card goes up, the volume side goes down, and vice versa. If volume increases, you notice that as volume goes up, pressure goes down. If we think about Charles' Law, where pressure is being held constant, we put the pencil through the P. Here we notice as volume goes up, temperature also goes up, so that side of the card goes up together. As volume goes down, or temperature goes down, the other one goes down also. The last one with Gay-Lussac's, we put the pencil through the V. We notice as pressure increases, temperature does also, and vice versa. So that's how this card works, and it's just another way for you to kind of check your work. The last law I want to go over today is Avogadros Law. So this was discovered by the same guy who came up with the idea of grouping atoms together. This is also Amedeo Avogadro. And he just proposed that if you have equal volumes of gases at the same temperature and pressure, they're all going to have the same number of particles, whether that's atoms or molecules. So what he said, too, was that volume and number of moles are directly proportional. So we have V1 over N1 is equal to V2 over N2. So here we just, like I said, with him, he said that if you have the same volume, have the same number of particles. So if you have a different volume, twice the volume, for example, you would have twice as many particles. In some cases, that would be molecules. Okay, so we're going to work through a problem like this. But again, you would expect this to be a direct relationship between the number of moles and the volume. Okay, so here we have volume and number of moles, and we'd see that's a direct relationship. Okay, so let's work through an Avogadro's Law problem. So we have on one side of our problem, we have our P1, V1, T1, and we're also going to have N1. P2, V2, T2, and N2. So we have for our amount, we have 4 grams. Okay, so I'm just going to write that as N1, even though it's not a number of moles, because that is our amount. We have a volume of 22.4 liters, and we have a temperature of 0 degrees Celsius and a pressure of 1 atmosphere. We have a final amount of 3.0 grams, and everything else is the same, but it's asking us what the volume is. So pressure is the same, and the temperature is the same. So we can get rid of pressure and temperature since they're staying the same. Now, I just want to point out here, since it does not ask for moles, and it doesn't give us moles in either situation, we can actually keep this in grams. So we would only need to get this in moles if one of them were in moles and the other one were in grams, or if it asked us to find the number of moles. So let's plug this into our equation. So we have our equation, which is V1 over N1 is equal to V2 over N2. And this is Avogadro's Law. Okay, so we can start plugging this in. So we have 22.4 liters over 4.0 grams is equal to V2 over 3 grams. Okay, so we're going to cross multiply to get V2 by itself. So we're going to get, and we notice here grams will cancel out since it's on both sides. So we're going to get 22.4 liters is equal to, and that's times 3 over 4 is equal to V2. So let's plug that into our calculator. So we have 22.4 times 3 divided by 4 gives us 17 liters. Let me erase this grams. And that is our final answer. And if we look, that is what we expect from the answer it gave us. And also when we think about it, we see here that the number of grams or the number of moles is increasing. Is decreasing, so we'd also expect the volume to decrease. Okay, so that's how you do Avogadro's Law problems. And so I want you to try all these problems. Just focus on the ones I tell you to do because there are some combined gas law problems on this sheet. So good luck.